in exercise 816, we're building off of what we went over in exercise 815, and that's namely that when you have different beta hydrogens, you can have some that are in more crowded places and some in less crowded places. And those beta hydrogens give you different alkenes. The ones in more crowded places give you more substituted alkenes, which are more stable. Those are the Zaitsev products. And the ones in less crowded areas give you less substituted alkenes. Those are the Hofmann products, which are less stable. But you can control which of those you get more of using a certain type of base. Now, what we saw in the previous problem was that if you use a skinny base, that skinny base can reach any of the beta hydrogens. And so it will give you your Zaitsev product, the more stable product most of the time. And you'll still get the Hofmann product, it just won't happen, it won't stick around as long, and so as a population you'd have less of those, because it's less stable. Now, for the bulky base, in the case of a bulky base, and we specifically went through potassium tert butoxide, TBUOK, in that case, it has a harder time reaching the more crowded areas, and so you don't get the more substituted product as much. That's the minor product. The less substituted product, the Hofmann product, that is the major product. So we went through this last time. We kind of went through the steps for predicting these. Oops. And this time we're going to just apply those to a sort of synthesis problem. Okay, just fixing that small spelling error there. So Hofmann with one M, F, and two N's. So this time we want to think about, in each case, we want to know what should we add? Should we add a skinny base like sodium hydroxide? That's what they're mentioning. But we could have also used sodium methoxide or ethoxide, or should we use a bulky base like potassium tert butoxide? And to do that, you would want to draw in the beta hydrogens. Now remember, the carbon that has the leaving group on it is the alpha carbon. Every carbon next door to that is a beta carbon. So we have 3 beta carbons here. Now notice, because we formed the double bond to the right, we took the beta hydrogen there. We took the beta hydrogen on that right carbon to get that product. That's the one that we want to take. But what other products could we have gotten? Well, we have 2 other beta hydrogens. We could have stolen this bond, could have gone there, and we could have gotten this double bond. Or the base could have stolen this hydrogen. The electrons go toward the leaving group, and that would have given us this double bond. Now notice that these last 2 are really the same. All I have to do is flip this over like a pancake, and I have that molecule there. So those are really the same. So just for the sake of simplicity, I'm going to just discuss one of those. So you have these 2. So those are your 2 possible products. Now if you think about the substitution there, this top one, if you think about the number of carbons bonded to the carbons in the double bonds, has 1, 2, 3, 4. So that is tetrasubstituted. Below it, those are the 2 carbons in our double bond. How many carbons coming off of those? 1, 2. That is disubstituted. And so this tetrasubstituted product is the more stable one, and that's called the Zaitsev product. The less substituted product is the less stable one, and that's called the Hofmann product. So, what they told us to make was the Zaitsev product. Now, if you want the major product to be the Zaitsev product, then you want to use a skinny base. Notice, if you use a bulky base, the Zaitsev product is the minor product. We want it to be the major product, so we're going to use a skinny base. We don't want the Hofmann product, we want the Zaitsev product, so we use a skinny base. Hydroxide is a skinny base. They asked us, should we use hydroxide or tert-butoxide? We're going to use hydroxide, because that's a skinny base, and that will give us the Zaitsev product as the major product. Okay, with B, we're doing a similar analysis, but in this case, it's actually the same type of molecule. The leaving group is different. So in this case, if you wanted to think about the places you could form the double bonds, now let's try to think about this. So far, you really want to be able to visualize the beta hydrogens. But if you're doing this very quickly, you can imagine just redrawing this carbon skeleton. Just draw that without the leaving group. You know that the double bond you're making is going to be involved with this carbon. How many ways can you make a double bond to that carbon? And it looks like there are 3. What you'll see is 2 of them are actually the same. But let's draw all 3. The 3 ways you can have a double bond to that carbon is down, in the middle, and to the left. So those are the 3 possible elimination products that we can get. It's a nice shortcut to draw it like that, but you do want to be able to think in terms of the beta hydrogens in order to remember a lot of other details for how the reactions happen. So in this case, of these, we have this one right here. And if you notice, that's actually the same as the one on the left. All we have to do is flip this one like a pancake, and we get the molecule on the right. So because it's a duplicate, I'm going to erase it. So these are our 2 possible products. Now, if you want to think about how stable these are, and which one is the Zaitsev and Hofmann product, then you'd put the 2 dots at the end of the double bond and ask yourself how many carbons are coming off of those carbons in the double bond. Well, on the left, you have 4. So that's tetra substituted. On the right, you have 2. So that's di substituted. So the one on the left is more substituted. That means it's more stable. That's the Zaitsev product. The one on the right is less substituted. That means it's less stable. That's the Hofmann product. Now they want the Hofmann product. So how do you get the Hofmann product to be the major product? You use a bulky base. If you use a bulky base, it won't be able to reach the more substituted beta hydrogen, and you won't get the Zaitsev product. The bulky base will give you the Hofmann product. And so that's what we'd use here. Now the options for the bulky base that they gave us was tert-butoxide. They said either use hydroxide or tert-butoxide. If we want the Hofmann product, we would use tert-butoxide. And that, remember, would just look like a tert-butyl group with an oxygen that has a full negative charge. So the tert-butoxide will give you this Hofmann product as your major product. You'll still get the Zaitsev product, but it won't be the major product. So when you're trying to make alkenes, if you have a leaving group and you want to turn the molecule, you want to into an alkene so that you have a double bond in the molecule, you can strategically place the double bond in different directions. In this original molecule, you could either make the double bond appear to the left or to the right by choosing a skinny base or a bulky base, using this sort of thought process that we went through here. Think about whether the product you want is the more substituted Zaitsev product or the less substituted Hofmann product. If you want the Zaitsev product, use a skinny base. If you want the Hofmann product, use a bulky base.